The user interface is how the end user views and interacts with the custom feature. As the author of the custom feature, you decide how the feature appears in the toolbar, what icon displays, if there are any tool tips, and all of the user inputs in the feature dialog. We are going to start the script for a dome feature that we will continue over the next few videos. The dome feature takes a circular face and applies a convex or concave dome to it. In this video, we will focus on getting the name, icon, and tooltip to display correctly. In a new document, create a new Feature Studio. Define a new feature. It automatically adds an annotation to define the name of the feature and a constant that contains the rest of the feature information. The feature annotation is what communicates to the rest of Onshape how this feature should appear. The feature type name is required for the script to be recognized as a custom feature. It is important to update the default values to text that matches the custom feature you are building. Edit the feature type name and change it to dome. There are several other optional annotations you can add. The filter selector declares what keywords would cause your feature to be retained in the feature list filter. The feature name template allows you to change the default naming convention used for new features in the feature list. UI Hint provides additional UI options. The option No Preview Provided ensures that the preview slider is removed from the feature dialog. This means as the user is entering inputs, the feature always shows the final result without the option to adjust the preview. Most UI hints are reserved for specific parameters within the precondition or for Onshape's internal use. The feature type description and description image are displayed in the Feature Tooltip and the Search Tools panel. Icon allows you to assign an icon to the feature. When no icon is assigned, Onshape displays the custom feature's name with initials. All of the feature annotations are listed out in the Feature UI section of the FeatureScript guide. Upload an SVG to use as the feature icon for the dome feature. A link to download the dome SVG is in the key takeaways for this video. In order to use it, we need to add an import to the top of the Feature Studio. At the top, add a unique identifier such as feature icon followed by a double colon. Select the Import button at the top and select the SVG under Files. It automatically populates the import information. Add the icon field to the annotation. Call out the feature icon identifier and use blob data as a placeholder for the import information. Add a feature type description annotation. In a Part Studio, the feature now shows with the correct name, icon, and tooltip. Let's discuss the most common parameters used in custom features. Boolean is a yes or no parameter. Booleans display as a checkbox, but can be changed to instead apply a direction toggle to another parameter. The string parameter creates a text box. The enum parameter creates a pull-down list with a selection for each enum value. The quantity parameter looks like a text box, but it is for other kinds of values, especially numeric quantities and values with units. The query parameter allows users to select entities within the context. The reference parameter allows the user to pick data contained in other Onshape tabs and documents. The array parameter allows you to create an array of items that can contain several subparameters. The user can add any number of items to an array parameter. Let's begin building the inputs for the dome feature. The precondition is where you put the user inputs for the feature dialog. First, add a query parameter to the precondition named face. It is important to add filters to ensure users can only select appropriate geometry. The selected face must be a planar face that is within a solid body. Entity type .face ensures it is a face. constructionObject.no and sketchObject.no. Ensure the selection is a face that is attached to a solid body. GeometryType.plane ensures the face that the user selects is planar. There should be only one selection for the dome, so leave the default max number of picks at 1. Changed my query to face. Next, define how the dome is shaped at the start and end. Add an enum named connection type to define the options, position and tangent. Create enum parameters in the precondition for the start and end conditions. Point them to the connection type enum. Additionally, add a start and end magnitude to allow the user to change the intensity of the curve of the dome. Add a quantity parameter that uses the isReal function. IsReal is a predicate that returns true when the value is a real number within the bounds specified. Set the bounds to positive real bounds. A full list of different types of bounds is in the standard library documentation. Create a similar annotation for the end magnitude. Parameter groups allow you to group inputs into collapsible groups. This helps simplify large dialogues with several inputs. Add parameter groups for start and end. Move the appropriate parameters inside each statement. Make sure the group name is set to a logical name. This is what will show in the group header. You can use if statements predicated on enums or booleans in the precondition to control parameter visibility. If the start or end conditions are set to position, then the magnitude is not needed. Add an if statement for both the start and end conditions. If the start or end condition is not position, add the parameter for the magnitude. Add an isLength parameter for the depth of the dome. It must be a positive number. Change the bounds to non-negative length bounds. Add a Boolean parameter to control the direction of the depth. To turn a Boolean into an opposite direction toggle, you must use a UI hint. Add a UI hint to the Boolean parameter so the user can reverse the direction of the dome if needed. Enter opposite direction as the value. In the Part Studio, test the feature dialog. First, create a cylindrical boss to test on. The query selection only allows a flat face selection. Each of the group boxes are labeled correctly and show the correct options underneath. The start and end magnitude parameters hide when position is chosen. The depth is a length parameter that has an opposite direction toggle. We built the feature dialog for the dome feature. First, create constants for each of the parameters in the feature dialog. This makes it easier to reference them in other functions. The peak of the dome should be offset from the center of the selected face. There are a few different ways to find the center of a face. Looking through the standard library documentation, you may be tempted to use a function like EV_approximate centroid, but it is not recommended to use any functions with approximate in the name to build geometry. A valid option would be to use the EV_plane function. We used this in a previous video. The origin is automatically placed at the center of the face's bounding box. A more direct way to find a location on a face is to use the EV_face_tangent_plane function to create a plane on the selected face where the origin is in the center of the face's bounding box. This function is similar to the EV_plane function, but gives you more control where the origin is placed. Create a constant named facePlane and set it equal to the result of a EV_face_tangent_plane function. Set the face parameter to selected face. Leave the parameter vector at the default, which will place the origin at the center of the face's bounding box. Create a new constant named center and set it equal to facePlane.origin. Offset the center to create the peak. Create a new constant named peakLocation and set it equal to center plus the product of depth and facePlane.normal. Multiplying the depth by the face's normal vector offsets the center point in the outward direction relative to the face. This accommodates face selections that could be at any angle with respect to the primary axes. Create a new constant named pointID. Set it equal to ID plus point. This is not entirely necessary, but is best practice since we will reference the ID in more than one place. Use the opPoint command to create a point at point location. Set the point parameter to peak location. Set the ID of the function to pointID instead of the default. Create the loft. First, create a constant for the loft ID. The OmpLoft function requires an array of subqueries to identify each of the profiles in addition to several optional parameters. Start an OmpLoft. Change the ID to loft ID. The loft will use two profiles, the selected face and the point created at the peak. They both need to be in query form. Since the selected face is a parameter in the feature dialog, it is already a query. The point at the peak is not. Create another constant named pointQuery and set it equal to the result of a queryCreatedBy function. Enter pointID as the argument. Remove the connections parameter. Enter the two profiles for the profile subqueries. Additionally, use opDeleteBodies to delete the point at the peak. Otherwise, the finished feature will show a selectable point in the model space. It takes in a query for the entity's parameter. Test the feature in a part studio with a cylindrical boss. It creates a lofted body, but there are a few things missing. First, the direction toggle does not work. Second, it does not automatically combine with the second body. And finally, the start and end types are not working. First, fix the direction toggle. Depth direction is dependent on opposite direction, so move the constant declaration below. Change the depth constant to use the conditional operator. If opposite direction is true, set it to a negative value. Otherwise, leave it as a positive value. Now the toggle works correctly. Use the opBoolean function to combine the original part with the loft. Op Boolean has parameters for tools, targets, and operation type. Additionally, there are several optional parameters. For a convex dome, the Boolean should be a union type. A concave dome would require subtraction. To achieve this, we need to use an if-else statement. Use opposite direction as the condition for the if statement. If opposite direction is true, execute a subtraction Boolean. The tools parameter of a subtraction Boolean is the body used to remove material. In this case, it is the lofted body. The parameter must be in query form. Create a constant and name it loft part. Set loft part equal to the result of a Q created by function. Set loft ID and entity type.body as its arguments. A subtraction Boolean also requires another parameter for the target. Create a new constant named selected part. Set selected part equal to the result of a QOwnerBody function. QOwnerBody returns a query containing the bodies that any of the given entities belong to. Set selected face as the argument. In the subtraction Boolean, set the tools to loft part. Create a new parameter, named targets, and set it to selected part. If opposite direction has not been toggled, the op Boolean should execute a union. The loft part and selected part need to be combined into one query for the tools parameter of the union. Create a constant named toolBodies. Set it equal to the result of a QUnion function. QUnion combines two or more queries into a single query. Enter loft part and selected part into the argument as an array. Set the tools parameter to the toolBodies constant. Targets are not needed for a union Boolean. In the Part Studio, the loft appropriately combines with the original part, either as a convex or concave dome. If you try to create a concave dome that is the same height as the boss, the feature errors out. Finally, add the necessary functions to develop the start and end types. In the opLoft function, the derivative info parameter takes in an array of maps to define shape constraints at the start and end profiles. Since the loft could be either position or tangent at either endpoint, it is necessary to create a variable we can manipulate based on conditions. Define an empty array named dinfo before the opLoft function. The derivative info is only needed if the user selects tangent for the start condition or end condition. Create an if statement that checks that the start condition is equal to connection type.tangent. In order to set tangency at the start profile, we need to select the faces that the loft will be tangent to. Create a constant named adjacent faces. Set adjacent faces equal to the result of a QAdjacent function. QAdjacent takes in arguments for the seed, adjacency type, and optionally the entity type. Set the seed to the selected face, adjacency type to adjacency type.edge, and the entity type to entity type.face to ensure the result only contains faces. Create a constant named start condition map. It needs 3 parameters. Profile index is always 0 for the start condition. Set magnitude to the start magnitude. Adjacent faces are the faces that connect to the profile. Set adjacent faces to the adjacent faces constant. Add the map to the dinfo array. Set dinfo equal to the result of an append function. Append takes in 2 arguments, an existing array and the new value. Set dinfo and start condition map as the arguments. Now create the appropriate functions for the end condition. Create another if statement for if the end condition is tangent. Create a constant named end condition map. It needs 4 parameters. Set profile index to 1 for the end condition. Set magnitude to the end magnitude constant. Since the loft is coming to a point, there are no adjacent faces to measure tangency. Instead, we will make it tangent to a plane that has the same normal vector as the selected face. Set the vector parameter to face plane.normal and tangent to plane to true. Append d-info with the end condition map. Add the derivative info to the op loft and commit the changes. Each of the inputs are now fully functioning. We saw that a concave dome that is the same height as the boss can cause it to fail. Additionally, certain face and dome geometries can cause it to fail or create undesirable geometry. The Boolean will fail for a concave dome if the dome is the same height as the boss it is put on. This is because it creates invalid geometry. Add try and catch statements around the subtraction Boolean. In the catch, use the report feature warning function to give a pop-up notification to the user. Report feature warning takes in 3 arguments: the context, feature ID, and the message you want to deliver. Enter a custom warning message. Test the feature. Now, when the dome is inverted and the error is triggered, a warning appears at the top. Use Add Debug Entities to highlight the loft part. If the Boolean is successful, nothing is highlighted. If the Boolean fails, the lofted part highlights in red. Warnings provide a pop-up notification, but they do not prevent successful parts of the script from executing. The parts list shows 2 parts instead of 1. This is because the loft is successful, but not the Boolean. Usually when a custom feature errors, you do not want it to generate anything at all. Comment out the warning and debug lines. Enter throw, followed by the regen error function. There are many different inputs allowed for the regen error function. For this feature, we will add an error string, faulty parameter, and entities. Enter the warning, depth, and loft part for the 3 arguments. The depth must be entered as an array. The regen error function cancels the entire dome feature when the Boolean fails. The depth parameter and entities highlight in red. Mouse over the depth parameter and it shows the message defined in the regen error. As we saw earlier, the feature can also fail with certain face profiles. Add another try catch around the op loft function that will also throw a regen error. Throw another regen error to highlight the selected face. In this custom feature, we did not need to use sketches, but many features do require them. Sketches are a part of the Part Studio's context, but take a very specific form within FeatureScript. Sketch objects are started with either the New Sketch or New Sketch on Plane feature. Then you can complete a series of sketch actions. Most sketch action functions are prefixed with SK. Complete sketches with the sksolve function. Without sksolve, nothing will appear in the context. In this video, we will make a custom feature that makes a circular notch on an edge. Start a new document and create a new feature studio. Add a new feature named Circular Notch. Add a query parameter for the user to select a linear edge. Add the filters geometry type.line and body type.solid. These filters ensure the selection is on an edge that is suitable for the notch. The notch width and radius are a function of the size of the edge. The width is 3/10 of the edge length and the radius is 1/10. Create a constant named edge length and set it equal to the result of the EV-length function. Enter definition.edge in the entities parameter. Create two constants for the notch width and radius to calculate their values with respect to the edge length. All sketches need a sketch plane in their definition. The notch should be centered on the edge, so we must create a plane that is perpendicular to the edge at the midpoint. To evaluate the midpoint and direction of the edge, create a constant named midline and set it equal to the result of the EV-edge tangent line function. Enter definition.edge for the edge and 0.5 for the parameter to put it in the center. The edge contains an origin and normal direction for the plane. Create a constant named midplane and set it equal to the result of the plane function. Use midline.origin and midline.direction for the arguments. There are two functions that start a new sketch. The new sketch function takes in a query parameter, so there must be existing entities in the context to define the sketch plane. If you use a plane or planar face to define it, the new sketch function places the sketch's origin where the part studio's origin casts onto the plane. If the query contains a mate connector, it places the origin on the mate connector. New sketch on plane takes in a plane parameter. This means you can define an arbitrary plane in FeatureScript that is not yet a part of the context to create the sketch. It also gives you more control over the origin, which is important for defining sketch entities. Create a constant named sketch ID for the sketch's ID because it is used in more than one place. Create a constant named sketch1 and set it equal to the result of a new sketch on plane function. We need to reference the sketch object with each sketch action, so it is necessary to assign it to a constant. Change the ID to sketch ID and enter midplane for the sketch plane parameter. This sketch only requires a circle. Use the skCircle function to create a circle. skCircle takes in two arguments for the center point and radius. Leave the default value for the center parameter to place it at the sketch's origin. Enter notch radius for the radius parameter. Finish the sketch with the sksolve function. Test the feature in a part studio. The sketch is positioned perpendicular to the edge at its midpoint. To create a cut, you need to combine an op-extrude with an op-boolean subtraction. Op-extrude contains many required and optional parameters. For this example, the cut should stay centered on the edge. This requires the entities, direction, end bound, end depth, start bound, and start depth parameters. The entities parameter requires a query for its input. Use the QSketch region query to reference the sketch face. Enter midline.direction for direction. Use bounding type.blind for the start and end bounds. The depth for each of them is half the notch width. Subtract the body created by the op extrude with an op Boolean. Use Boolean operation type.subtraction for the operation type. The tool is the body created by the op extrude. Use Q created by to enter it into the parameter. The edge is an entity of a part body. Use Q owner body to grab the part for the targets. Add the op delete bodies function to delete the sketch so it is not visible when the feature is completed. Commit the code and test the feature. It works well if the profile is a circle, but if you have a more complex profile, the orientation of the sketch becomes more important. Open the document with the circular notch feature from the last video. If you are not following the videos in order, copy the sketching document linked in the key takeaways for this video. Copy the feature studio containing the circular notch. Name it rounded notch. Instead of a circle, we are going to change it to a profile where the X and Y directions are more important. This profile will look like a slot. Only a quarter of the profile is ever in contact with the solid, but making the profile symmetric prevents you from having to add logic to flip the positive X and Y directions. The notch depth is a function of the length of the edge chosen. The arcs are defined by endpoints and a peak. The peak of the arc is 2 times the notch depth in the Y direction. In the Feature Studio, remove the notch radius. Add constants for notch depth X, notch depth Y, and fillet peak. Remove the SK circle function and add an SK rectangle. Once we draw the arcs, Onshape will ignore the vertical lines of the rectangle because it only cares about the overall enclosed region. Enter a vector with the values negative notch depth X and negative notch depth Y for the first corner and a vector with the values notch depth X and notch depth Y for the second corner. This centers the rectangle on the origin. Use 2 SK arc functions for the arcs. The end points need to match with the corners of the rectangle. For the first arc, the mid parameter is a vector with the value of negative fillet peak for the X and 0 inches for the Y. Change the ID of the second arc to be unique. For the second arc, the mid parameter uses the positive value of fillet peak. There is an SK constraint function to relate entities, but it is usually unnecessary for programmatically created profiles because they are never user-edited. Rename the feature to rounded notch. Test the feature. You currently have no control over the orientation of the profile. The X and Y directions can flip for different selections. To add more control to the behavior, you need to properly define what's considered the positive Y direction for the notch profile. Add a new query parameter to the precondition. Name it Y direction. Add query filter compound. Allows direction for the filter. This allows the user to select anything that can define an axis, such as a cylinder, circle, edge, face, and more. Change the identifier to definition.direction. Create a new constant before the mid-plane constant named y-direction. Set it equal to the result of an extract direction function. Extract direction returns a unitless vector for direction. Enter definition.direction as the argument. Previously, the mid-plane definition included only the origin and normal direction. This allowed the profile to rotate, sometimes unexpectedly. To further constrain it, you can add the x direction to the arguments. The y-direction constant defines y, and mid-line.direction defines z, but we do not have x. Use the cross function to cross-multiply vectors for the y and z directions to get the x direction. Commit the changes and test the feature. The flat face of the notch is always perpendicular to the direction defined for y. This gives the user control to make sure the notch is always appropriately oriented. To improve the user experience, you may want to add regen error functions to test if the edge and direction are selected. These will improve the user experience to enable users to make the correct selections.